Let's talk about the secant method, one more method to find the root of an equation. If there is a function, we are looking for the point where the function value is 0. And how can we do? We can, instead of using the tangent, we can using a straight line connecting 2 points of the function, and the root of that straight line is an approximation for the root of the function if the points we are using are close enough to the root. Okay, so the major disadvantage of Newton's method is that we need the derivative on top. And if you think about an algorithm implemented in MATLAB, then you have to provide the derivative. MATLAB cannot find the derivative by himself. Or Excel, think about Excel. How could Excel implicitly find a derivative? That is not possible. So if you want to use this algorithm, the Newton algorithm, you have the user to provide the derivative, and that is not acceptable. So instead of the tangent, we can approximate the tangent with a secant. A secant is that you have 2 points and you connect them with a straight line, and that's a secant. And now let's find the root of the secant. So the first step is, what is the secant? Connecting these 2 points. Okay, so we start with the function value of x1, and then we say this is the slope of the secant of the line connecting these 2 values. You subtract the function value and you subtract the corresponding arguments. Okay, and you can write it that way, or you flip x0 and x1 on the numerator and the denominator, and then, as you can see, if you have this situation, you can flip 2 minus 7 and 5 minus 3. This is the same. So, okay, this is the slope and this is the deviation from x1. So if this is the secant, it has to pass through our 2 points. If you use for x1, then this is 0, so indeed you have f of x1, this value. And if you are using x0 here, then these 2 cancel, then this cancels, and then you get f of x0, and that's what you want. Okay, so we have a linear function passing these 2 points, and now we want the root of this secant, and the variable is x, x1, x0, f of x1, f of x0 is some number, not a variable, but x is the variable. So set this expression to 0, bring that to the other side with a minus, and then multiply by this fraction with swapped numerator and denominator. Then it vanishes from the left hand side and it shows up on the right hand side. And then bring that to the other side with a plus, and you end with that. Now this is the root of the secant. So if we have x0 and x1, this is our new x2. And we can iterate that process. So instead of x0, we have xn minus 1. Instead of x1, we have xn. And then this is our xn plus 1. And we get this recursive sequence. Okay. And the hope is that the approximation will improve. We will come closer to the root. Okay, and we could test the function values if they really decrease or not, but we will not do so in our code. So this expression you can rewrite. You have a denominator and then expand that x and also to a fraction with that denominator. And if you do the calculation, I invite you to do that. It's a good training. When I was a student, I always did these steps by myself and tried if I'm able to do that. Then you can write this also in that way. This is exactly equivalent, but it's not clear from the first sight, but from the second side it is. Okay, so this is our recursion. And then for this function here and this starting point x0 and this starting point x1, we see the following. Take the secant, take the root of the secant, and then forget x0, and these two are our new x0 and x1. So let's find the secant through these two lines, find the root of that secant, and then forget x1, and you have a new x2 and x3, and then find the secant, find the root of the secant, and in this example here we see now we are very, very close to the root. And what do we see? We see in this case we started with 2 points where the function values are of different sign. In this case there must be a root is guaranteed, and then we forget x0, and now we have a situation we no more have 2 points with different sign of the function value, but that does not matter. Okay, we can sum here what our analysis told us. This is the secant method, and this is a very simple algorithm, more simple than the Newton method, because we no more need a derivative. And what is the rate of convergence? We can analyze, as we will do in one of the next videos, that we no more have quadratic convergence. Newton's method is quadratically convergent and the secant method is not. But the rate of convergence is 1.618, and it doesn't matter, that's what I want to say, it doesn't matter that this is less than 2, because if you perform 2 steps means square this number, and this is more than 2, so it does not really matter that it's not quadratic. If you perform 2 steps of bisection, linear convergence is still linear. The factor improves, but it stays to be linear, so the trick of performing twice the algorithm twice does not help to come from linear to super linear. Okay, we will talk about that later in more detail. The user must provide initial points once more. Bisection was of that type, Newton was of that type, and the secant method is again of that type. The user has to provide initial points, and that's a disadvantage because they need to be good, close enough to the root we are looking for, especially in the situation that you have a function with several roots, and if you want to find all of them, you have to provide 4 times starting values, initial values, which are close to the corresponding root. But what if you don't know that there are 4 roots and you don't know where they are? How can you provide appropriate starting values? This is a hard question, unfortunately. The method can find only 1 root. If you want to find more than 1 root, you have to provide more than 1 set of starting values, and do the algorithm with the corresponding starting values. Okay, this is the implementation as I implemented in MATLAB code or in Octave code, and we can call it that way here with an implicit function. The alternative is to write an M file, and then you can call that M file. If you don't know what I mean, please ask me, and we can talk about that in detail. That is really important to understand that basic stuff. Okay, so let's use our algorithm to our 3 problems. We checked the first problem is the logarithm of x minus x divided by 3, and let's use initial starting values 0.1 and 1, and we know that between 0 and 1 there is a root. And if we call root secant, we introduce that line, and we have this comma and this comma instead of a semicolon, and then we will have some output running that code. We will see this because of that line and that comma, and we will see that because we are using commas instead of semicolons. It's more convenient than in Python is. In Python you need a print. In MATLAB you have to replace a semicolon by a colon, and then you see some output on the screen. Okay, and what do we see? After 8 steps we found a root, and we found the root we were looking for. But when I said there's a root between 0 and 1, that was wrong. There's a root between 0 and 3, okay? And we found that root after 8 steps. And we don't need that. I had it here because I copied from the Newton method. We don't need the derivative. That's a big advantage. We don't need the derivative. Okay, so let's go to our second example, and again I copied from Newton's method, and we don't need that line rope around the earth extended by 1 meter. How far can you lift? And here we calculate the corresponding angle. Check the video we had about that topic. And then look for the root between 0.1 and 1, let's say, and then you find after 23 steps, unfortunately it's 23 steps to find the root, but then we found the root we are looking for. I recommend don't read that like a book, but do that with the help of your electronic calculator. Please do the steps on paper together with your electronic calculator and find, in this case, 0.099957 to be the x2. And then find x3, and this will be that number. Reproduce these numbers on your paper, and then you are 100% sure that you really understood. Or maybe you implement the logic of the secant method in Python or in some other programming language. Then you can use that as an example. You can run your code and you can check if you reproduce exactly the same numbers, and so you can check if your code might be correct. This is again the rope around the earth. In this case we use the tangent version, okay, and in this case after 18 steps we found the root we are looking for. Unfortunately a lot of steps, but this has to do with the nature of the root. We don't have the situation that the derivative at the root is unequal to 0. It is unequal to 0, but very close to 0, and so convergence is very slow, unfortunately, in that case. So maybe the better example is this one. The more typical example is this one, and then you see very few steps are enough to find the root.